elements are present. As the number of elements goes up, the molar mass goes up. Notice the boiling points also rise. You do not need to copy the numbers. That's irrelevant. Just understand that the intermolecular forces go up as the number of compounds go up. Of course, if I was comparing two compounds with the same mass, but one of them had a polar group, for example, if I compared these two compounds with roughly similar molar masses. This one, there's 12 and then 6, which is about 12 and 12 is 24, and 6 more is about 30. This one is 16 and 12 is 28, 29, 30, 31, 32. So the molar masses are very similar. Which one of those two would have the higher boiling point by far? Why? Because of the hydrogen bonding. So you have to understand, a homologous series will all have the same polarity. You won't be comparing weird polarities. You're comparing size and shape. Do you understand? Some questions will have you compare the functional groups and their polarities. So you need to understand how polarities work. So if molar masses are the same, London dispersion forces, van der Waals, are the same. And so we fall back upon polarity. The higher polar thing will be higher intermolecular forces. You guys okay with that? Okay? All right, good. Then we're almost done. I just wanted to show you a diagram here. This is one of the standards you're asked to study is that of what a structural formula is and how to see it, what a condensed structural formula is. This side over here you don't really need to pay attention to. It's these two, and I realize they're fairly small, but I just wanted to point this out. This is what we've been doing. It's called the structural formula. They're showing the H's. And what they have written here, let me write over the top. Here's what they have written here. And I wanted you to see some of the symbols you're going to see. So here in this thing we have CH3, we have CH2, CH2, CH2. They are showing that as CH2 in parentheses with the subscript of 3 outside. So please understand that means that there are 3 in a row attached to the previous. And here's a rule you can take home with you. If there is something in parentheses with the subscript outside, that thing is attached to the carbon in front of it. Okay, I'll say that one more time. If you see a compound in parentheses like this, in one of these condensed structural formulas, if you see a compound written in parentheses with the subscript outside, that is telling you that those 3 are attached in sequence to this in front of it, to the carbon in front of it. The only time that would be violated is in the case like right here, where they are written first, but the same rule applies. The rule I stated was that whatever is in parentheses would be attached to the carbon in front of it. Well, there is no carbon in front of it, so it's got to be attached to the carbon to the right of it. Agreed? So here you see, for example, I'll write it a little bigger for you. Now you have to understand the octet rule to translate these. 2 CH3s, if they were attached to each other, this is what we would have. There should be H's. Now, that compound is complete. Both of those carbons have octets. This is an H, so the rest of this could not be attached. So you have to understand that by putting it in parentheses, they're saying that they are individual things attached to something else. They're attached to the next available carbon. So this is not that. It is a CH3 and a CH3 both attached to a carbon. This carbon. And that carbon is attached to another carbon. This H is attached to that carbon here. This H has, excuse me, that carbon has 2, and then OH, which is right there. Good luck. You're welcome. Okay? So those are called condensed structural formulas. This chart will be a part of the video, so I'll just scroll through the whole thing so you can see it. Just look it over, practice a few if you want outside of class to get an idea of what that is. Okay? Any questions on those things? Okay, good. This one's going to go quick. This refers, if I didn't say so earlier, that refers to the curriculum point. Solubility and volatility. What does solubility mean? Dissolve in water. Volatility means evaporate. Okay? So what is the rule we use to decide if something dissolves in water? What's that common phrase we say? You guys are tired. Okay. I'll get off your back. Like dissolves like, right? Like dissolves like. Polarity, things that have similar polarities are like each other. They tend to mix. Agreed? And if you're not tired enough to forget this, remember the reason for that is when the solute and solvent interact, if they have similar polarities, there is a very favorable interaction in that step, which is enough to compensate for the unfavorable separation steps. Maybe you remember that, maybe you don't. Hopefully something is jogging your memory. So these are both related to polarity. It's very simple. So remember, water, let's talk about the issue of solubility. Water is polar. Period. So things that are polar will dissolve in water. Period. End of story. So what do you think? Will alkanes dissolve in water? No, because alkanes have this bond or they have a lot of this bond. Neither of which is polar. Very non-polar. So alkanes, not polar, not very soluble. Alkenes, they are not polar, not very soluble. Alkynes, not polar, not very soluble. It's a very simple concept. But how about alcohols or aldehydes? Polar or non-polar? You tell me. Polar. Very polar. This is a hydrogen bonding issue. This bond here is polar. This is definitely polar. Carboxylic acids, definitely polar. So what do you think? Soluble or insoluble? Soluble. It's a very simple issue. Now, we have to combine that idea with that of the homologous series thing that we discussed earlier. So let me do that, and we'll end on that note. Okay? I think it's fairly simple to see that things that have polar groups tend to be soluble in water. Things that do not tend to be insoluble. Would you agree? And by the way, if volatility is a measure of how well it evaporates, are chemicals that have a very high volatility, do they have strong forces between them or weak? Weak. So chemicals that have very low polarity tend to be very volatile. Agreed? So alkanes, we've just discussed, are not soluble. They are not soluble because they're not polar. And if they're not polar, they should have very high volatility. Agreed? So here are some common alkanes. See if you recognize these names. Methane. How about propane? You ever heard of propane? Is propane a liquid or a gas? Go turn on the Bunsen burner things and you tell me. Propane is a gas. Do you understand? Why is it a gas? Because its intermolecular forces are low. No, they're not. We don't say their forces are volatile. Their forces are very low, very weak, which means it's very volatile. Do you understand how that works? Things that are polar tend to be sticky, tend to be liquids at room temperature. Do you understand? So they're not very volatile. So there's a very close relationship between solubility and volatility. Very close. It's through polarity. However, if we take our alcohols as an example, methanol, ethanol, propanol, butanol. Of course, this would be one propanol and one butanol. What is this series called? A homologous series. Excellent. Are these soluble in water? Okay. Do they have polarity? They have hydrogen bonding. Is water polar? If they have like polarities, they tend to dissolve in each other. Agreed? But wait a minute. As the number of carbon atoms grows, if I add yet another carbon atom, aren't they gaining more and more nonpolar character? This is an important issue. Does everyone understand how the number of carbons increases? Now we have more interaction between nonpolar sections. So how do you think adding more carbons which are nonpolar, How do you think that affects how much of this chemical dissolves in water, which is very polar? Do you think that has an effect? It does. As the number of carbons goes up, the polarity gets less and less like water and more like something like oil. Do you understand? Because oil is nonpolar. So the solubility up here for the very short ones is very high. And as we go down the list, the solubility begins to decrease because it's getting less and less like water. More and more like oil, for example. Do you understand that issue? Does anybody not understand? Okay.